Dear friend, I am here to find deflection at point C of this simply supported beam, which is subjected with a concentrated moment at support A, and we need to find deflection at C of this simply supported beam. And the method used for this deflection calculation will be conjugate beam method. There are other methods to calculate deflection like unit load method, strain energy method, and moment area method. And as per my experience, I find I can understand this method is very easy to solve this kind of problem, because by directly calculating bending moment at any desired point where you need to find deflection in a conjugate beam, the respective conjugate beam of a real beam, it will give directly the deflection at the same point of a real beam. So uh, as per conjugate beam theorem, any real beam that is the simply supported, the conjugate beam will be of the same kind. So conjugate beam of this real beam, this is the real beam which is our subject of analysis. There is a support A, a support B, and there is a point C where we want to find deflection at C, and this point support A is subjected with a concentrated moment m0. So its corresponding uh, conjugate beam will be, that is the imaginary beam through which we will find a deflection at same point C. This is the point C, this is the point A, this point is B, this point is C. This is the real conjugate beam of this same simply supported beam. Length of this beam is L0. The length will be same here also. And for finding deflection at C at any point of a real beam, we need to find bending moment at the same point of a conjugate beam, and that bending moment will give the deflection at the same point of a real beam. So in order to find bending moment at any point, here our subject of analysis is to find the deflection at point C. So here we need to find the bending moment of this conjugate beam. This is the real beam, this is the conjugate beam. To understand the concept how the conjugate beam is formed for a real beam, you need to go for any textbook. Here I am not going to discuss on that at all. Now to find bending moment at any point, here we need to find the bending moment at point C. We need to form a loading diagram over this. So as per the conjugate beam theorem, the M over EI diagram of a real beam will be put directly on this conjugate beam to make its loading diagram, and according to this loading diagram we need to find the bending moment at the desired point. So we will finding, after forming a loading diagram over here on this conjugate beam, we will find bending moment at C, and it will give directly deflection at C of a real beam. So let's continue. Our real beam is here. This is the real beam, this is the real beam, and this point support is A, this support is B, and there is a point C, and the length of this beam is L, and this is subjected with a concentrated moment of n0 in clockwise directions, and here respective conjugate beam will be of the same nature. Here support A, here is support B, and there is point center of this beam C, length of this beam L, and this is the conjugate beam, this is the real beam. We need to develop a loading pattern, or you can do loading diagram on this conjugate beam. As per the conjugate beam method, the M over EI diagram for this real beam will be put on this conjugate beam to make its loading diagram. So here we are going to draw M over EI diagram for this real beam. Before drawing M over EI diagram, we need to form a M diagram, that is the bending moment diagram. So bending moment diagram will, every coordinate of this bending moment diagram will be divided by a constant value of EI, that is the flexural rigidity, to form a M over EI diagram. Now I am going to find bending moment diagram. Formation of M diagram or bending moment diagram. Here beam is subjected with a concentrated moment of m0, length is L, the center of this beam is C at a distance of L by 2, and its support is A, this support is B. Now as per the equilibrium condition of moment, summation of all moment about A will be 0, and from the equilibrium condition of loads, total load, vertical load will be 0. Therefore RA plus reaction at RA and reaction at B, RB will be 0, as there is no load is acting, there is no vertical load is acting over here. And another equation will be sum of moment about A will be 0. So as per our assumptions, we are taking anticlockwise moment as negative here. So RB, reactions RB, here is the RB, here RB will be acting, and here RA will be acting, and RB will be creating a anticlockwise moment about A. So here minus RB multiplying with this length L, as it is creating anticlockwise moment, so it will be with negative sign, and there is no other load is acting in this entire span of this beam, except there is a clockwise moment of m0 which is concentrated at point A. So clockwise moment will be positive, m0 will be 0. This is the equation. So RB will be m0 divided by L. RB equal to m0 divided by L. This is the moment at point B. These are reactions at B, m0 divided by L. Now as per this equation, RA plus RB equal to A, RA plus RB equal to 0. So RA equal to minus RB. Therefore RA will be minus m0 divided by L. As you see here, reactions at RA is negative. So as per our assumptions, we have taken reaction in opposite in upward directions, it will be in downward directions. So this beam will be converted in this form. Here we have calculated reactions RA equal to minus m0 by L and RB equal to m0 divided by L. These are the reactions we have calculated here. RA equal to minus m0 divided by L, RB equal to m0 divided by L. So as we have taken beam something like this, RA was taken in upward directions and RB was taken in upward directions, and moment m0 in anticlockwise direction. But here this beam will be changed according to reactions calculated, because reactions RA is in negative directions with negative sign, so it will be showing in downward direction. It will be RA here, and RB will be in upward direction, and length of this beam will be same. This length is same as it was earlier. This length will be same, and this is the point C. This point is A, this point is B. This point is A, this point is C, and this point is B. So, and RB value equal to M0 divided by L, and R equal to M0 divided by L. Now, for finding bending moment diagram, we need to find a general expression for bending moment so that we can draw a bending moment diagram. So let's take any section XX here, resistance of X from point B. So we are taking the free body diagram right of this section XX. Here will be the free body diagram. This point is B, and this is the section XX, and this length is X, as we have taken here, and there is a reaction. RB is acting in upward direction here, and value is M0 by L, M0 divided by L. So we need to find a moment at section XX. Let's suppose there is a moment of MXX which is acting at section XX, which is at a distance of X from point B, and this I have taken as per my initial observation that it is in clockwise directions. So we are going to take moment about this section XX. Therefore we are taking another point. That suppose this point is, we have taken A, B and C. Suppose this point is D. So according to the conservation of moment, or we can say according to the equilibrium equation of moment, sum of moment about any point is 0. So summation of moment about D will be 0, and about this point D there is a moment created by RB which is in anti-clockwise direction. So it will be minus RB multiplying with this distance X, and there is a clockwise moment which I have assumed in clockwise direction, so it will be in positive direction. It will be MXX, and there is no any other load is acting on this beam, this free body diagram of length, this beam of length X. So there will be no any moment, any another moment apart from this two moment. So it will be directly 0 here, and you can say RB value is nothing but M0 divided by L. This value is M0 divided by L. So in place of RB we will put minus M0 divided by L multiplying with X plus MXX will be 0. Therefore MXX, moment at section XX, will be M0. It will be positive in right of this equation, M0 divided by L into X. This is the general expression for moment at any section which is taken from point B, and you can say its MXX is directly proportional to X. MXX is directly proportional to X. It means moment at any section from point B is varying linearly. So you can see a bending moment diagram will be of triangular shape. It will be here. You can see here as we have drawn as our real beam is here. Here is RA. Value equal to M0 divided by L. There is a reactive force RB which is equal to M0 divided by L, and length of this beam is L, and there is a point C here. This is point B and this is point A. and moment, general expression of bending moment at any section xx has been calculated here, and mxx was, as per this expression, m0 by L into x, m0 divided by L into x, m0 divided by L is constant, so mxx is directly proportional to x. So let's take here at point B, at B x will be 0, so moment at B, which will be designated as MB, will be, in place of x we will put x equal to 0, so here MB will be 0. At C, center of this beam is C. At C, x equal to L by 2 here, so MC will be m0 from this expression, m0 divided by L in place of x. In place of x here we can put value of L by 2, and L by LL cancel, it will be m0 by 2. And here at A, x will be L, so moment at A will be MA, and from this expression, in place of x we will put L, so m0L into, in place of x we will put L, so here LL will be cancelled and it will be m0. So bending moment diagram will be here, this is the base of, this is the length of this beam here. Here this is this point A, this is point B, and this point is C, center of this beam. This length is L by 2, and this length is L by 2, and bending moment profile will be this. Here MA equal to m0 will be this at center of this beam. Here value will be m0 by 2. This is the bending moment diagram for this real beam. Now we are going to find a m over ei diagram for this same real beam, so that this m over ei diagram will be put on the conjugate beam to make its loading diagram for a conjugate beam. As per our analysis, we have done with the bending moment diagram. Bending moment diagram is here. Here is the M diagram, or you can say bending moment diagram. This is the M diagram, and I am going to redraw it. This point is A, this point is C, this point is B, this length is L by 2, this length is L by 2. Here moment value is m0 as we have calculated here, and here is m0 by 2 at the center of this beam. Here moment is m0 divided by 2. This is the M diagram. You can say this is the M diagram. Now M over EI diagram we are drawing here. Since M over EI diagram is drawn by dividing every coordinate, y coordinate of this M diagram with a constant value of EI, so its profile will be same, but this value will be somewhat less in M over EI diagram. So here profile will be same. The point is, this will be the point A, this point will be B, and this will be the point C. And here, as we are going to divide M divided by M0, M0 divided by constant value of EI, this is a flexural rigidity to form a M over EI diagram. So it will be M0 divided by EI. This is the M0 divided by EI. And here at C, the value calculated is m0 divided by twice EI. Here calculated value is m0 divided by twice EI. at C. Now this is the M over EI diagram. M over EI diagram. As I have told you, the real beam this is the real beam and this is the conjugate beam, and in order to find the deflection at point C, we need to find bending moment at C of this conjugate beam, and the M over EI diagram of this real beam will be directly put on this conjugate beam to make its loading diagram. So as you know, our real beam is this one. This is a real beam. I am again redrawing it. This point is A, this is B, this point is C. A clockwise moment of M0 acting here, and its conjugate beam will be, this is the real beam. Real beam, conjugate beam for this beam will be, here will be, and this is the M over EI diagram of a real beam. M over EI diagram of real beam. So M over EI diagram will be put here to make its loading diagram. Length of this beam will be L. This point is A, this point is B, and the value of this loading is M0 divided by EI. M0 divided by EI, and at point C, here is the center of this beam. Here the M over EI value is M0 divided by twice EI. Here you can say M0 over twice EI. This is the value of loading M0 divided by twice EI at center of this conjugate beam. This is a conjugate beam. Conjugate beam. Therefore, if we are able to find the bending moment at C of this conjugate beam, then it will give directly the deflection at C of a real beam which is subjected to the concentrated moment at point A, at support A. So now we are going to find the bending moment at C of this conjugate beam. Here you can see this is the conjugate beam. Conjugate beam is here. This is the conjugate beam having loading diagram. This is the loading diagram. As you have directly put the M over EI diagram to make its loading diagram, and loading value is here. The maximum value is M0 divided by EI at support A. This is support A, this is support B, and this is the center of this beam. And we are going to find the bending moment at C. Here the length of this beam is L, and this value is M0 divided by twice EI. As we have calculated here, M0 over twice EI, value at point C, and value of load at A is M0 divided by EI. This is a triangular loading, and we want to find bending moment at C. So we are taking a free body diagram at right of this section C, right of the point C. So it will be something like, now we need to find the reactions RA and RB here, so that we will be able to calculate the bending moment. So now we are going to find reactions RA and RB. Some of the vertical load Fy will be 0 as per the equilibrium equation of vertical load, and there will be conservation of moment, or you can say equilibrium equation for a moment we're taking about point A, so summation of moment about A will be 0, hence Fy will be what? Summation of all vertical load will be the total area of this load will give the total load and reaction in upward direction, so Ra plus Rb will be equal to area of this loading diagram. This area can be calculated very easily. It is a triangular load, so it will be half multiplying with this length L, and height of this triangular loading is m0 divided by ei, so it will be m0 L divided by twice ei. This is the reaction Ra plus Rb. This is the equation 1, and from this summation of moment A, and we are taking anticlockwise moment as negative, so Rb will be creating a moment which is in anticlockwise, so here we can see minus Rb into this length L will create an anticlockwise moment, and this loading will create a clockwise moment about this point A, and this area of this triangular loading will be giving a total load half into L this length, and m0 divided by ei will give total load, and total load will be acting at the, and centroid of this total load will be acting at a distance of L by 3. This is the L, so 1/3 of this length, this is the total load will be acting here, so here L divided by 3 will be the centroid of this loading diagram, so total load multiplying with this centroid will give the moment about this point, which will be in clockwise direction, and it will be 0 as per this moment about A. So Rb into L will be, here you can see m0 L square divided by 6 ei. Therefore Rb will be, here L will be cancelled, and it will be m0 L divided by 6 ei. This is the reactive force at point B, reaction Rb as per the equation 1. Ra plus Rb equal to m0 L divided by twice ei. So Ra will be from this m0 L divided by twice ei, here is a minus Rb will be m0 L divided by 6 ei. Now it will be 6 ei 3 m0 L minus m0 L, so it will be twice m0 L divided by 6 ei. 2 divided by 6 will be 3, so it will be m0 L divided by thrice ei. So two reactive forces Ra and Rb has been calculated, so we can summarize here. Ra equal to m0 L divided by 3 ei, and Rb will be equal to m0 L divided by 6 ei. This is the reactive forces for this conjugate beam. Here I am done with the reactive forces for Ra and Rb. So now our main objective is to calculate the bending moment at C of this conjugate beam, so that it will give directly the deflection at C of this 4 corresponding real beam. So now here I am going to redraw the all external loading with calculated reactive forces in a conjugate beam, so that it will be easy for you to understand how to calculate the bending moment at C of this conjugate beam. This is the support, and here RA is calculated here M0 L divided by thrice EI. Here is RB calculated is M0 L divided by 6 EI, and this point is A, this point is B, and this conjugate beam is subjected with triangular loading, and maximum loading is here. This value is, you can see here, this is the M0 divided by EI, so it will be M0 divided by EI. Here loading value at C will be M0 divided by twice EI. Loading value at C will be M0 divided by twice EI. Here we have calculated during the formation of M over EI diagram. Now we are going to find the bending moment at C. So take free body diagram of right part of point C here. So we can draw, this is a free body diagram. Here reactions will be, and this will be the loading diagram. This length is this is the reactive force RB equal to M0 L divided by 6 EI. Here length is L by 2. This is a free body diagram, and I am extending it to make you clear that we are doing for the same beam with a dotted line. Here it will be RA, this value is M0 divided by EI, and this value here is M0 divided by twice EI, and we need to calculate a bending moment at C. This is the point C, and this we are assuming this bending moment will be at C will be in clockwise direction, and we need to find this bending moment so that deflection will be calculated for the real beam. MC will be what we need to see here. So now this is the triangular loading. This is the point A, this point is B, and center of this beam is C, and there is a triangular loading from C to B. So area of this loading multiplying with the centroid will give moment. Now we can take moment about point C. Let's take moment about point C. Summation of moment about point C will be 0 at the sum of the all moment as per the conservation of moment will be 0, equilibrium equation of a moment. So RB will be creating an anti-clockwise moment about point C, so it will be minus RB into length will be L by 2 here, L by 2, and this loading diagram will create a clockwise moment, and this loading diagram will give a clockwise moment, and area of this loading diagram will be giving the total load, and this load will be acting at a centroid of this loading diagram. This will be acting at a length here. This length will be this length will be 1/3 of this length is L by 2. This total load will be acting. This is the total load, and total load will be area of this triangle. Total load will be area will be half into L by 2 multiplying with this height n0 divided by twice ei. So it will be n0L divided by 8 ei. This is the area of this loading diagram. So it is the total load, and total load is acting at a distance of 1/3 of this length L1, L by 2. So it will be L by 6 here. This is the centroid of this total load. So this load is creating a clockwise moment. So minus RB into L by 2 plus, as it is in clockwise direction, will be N0 L divided by 8 ei. The total load is acting at a distance of L by 6 from point C. So it will be L by 6, and it will be 0 as per the summation of all moment about C. But RB is equal to M0L divided by 6 ei. So we are extending this equation here. So in place of RB we can put here M0L divided by 6 ei. Then we can write here, and there is another moment MC which is acting in clockwise directions. There is another moment MC which is our object of analysis. So as it is acting in clockwise direction, so it will be MC, then it will be 0. This is the complete equations for calculating bending moment at point C. So here MC will be, just rewriting this, it will be RB will be our right side of this equation, sign will be with positive, RB multiplying with this L by 2, and it will be with minus sign. So it will be M0L divided by 8 ei multiplying L by 6. In place of RB we can put this value. This is the total load. No need to confuse total load of this triangular load. So in place of RB it will be M0L divided by 6 ei multiplying L by 2 minus, it will be M0L square divided by 48 ei. So it will be M0L square divided by 12 ei minus M0L square divided by 48 ei. Here we can rewrite the bending moment calculated MC, which is at the center of the conjugate beam, which will be M0L square divided by 12 ei minus M0L square divided by 48 ei. We can write it 48 ei is the LCM, and 4 M0L square minus M0L square, it will be 3 M0L square divided by 48 ei. So it will be 3 divided by 48 will be 16. So it will be M0L square divided by 16 ei. This is the bending moment at center of conjugate beam. This conjugate beam is the conjugate beam of a real beam of same span, which is subjected with a concentrated moment, and this bending moment calculated at C, at center of the conjugate beam, is the deflection delta C in real beam. And from the conjugate beam method, it's very easy to find out deflection at the desired point if we are able to find bending moment at the same point in corresponding conjugate beam. So here deflection delta C has been found as M0L square divided by 16 ei. I hope this entire concept might have clear to you. For any ambiguity and for any difficulty to understand the concept, you can write in comment box. I will obviously answer to you, and Dear friend, thanks for watching. Keep sharing to your friends and colleagues. Thanks.